All right, good day, everyone. What today we're going to be doing is the second part of 16.1. The first part had to deal with a unit circle, talking about how it's derived. In class, we talked about how we can use the unit circle, but now we're going to be talking about some special cases about this actual unit circle itself. Okay. Within this idea, we want to truly understand, like, how can we reference everything about the unit circle? Okay. So one of the key things that we're going to be talking about, and one of the most important things about the unit circle, is how even though that this thing is split into four separate quadrants where it goes 1, 2, 3, and 4, each of these quadrants are actually related in some way. And this picture actually does a really good job of describing that. If you notice, what they basically are doing is they're creating this triangle built into this unit circle, where at that top coordinate after the radius, we have a value of both x and y. Okay, we talked about the other day how we can solve out those values of x and y using our cosine values or even using our special right triangles to basically get a set portion of data. But the interesting thing enough is that that one triangle could basically help us describe four other problems or four other coordinates within this within this unit circle. Okay, what that basically means is if I know what these two are equal to, then I need to do basically zero math to figure out what these two should be equal to. Okay, this coordinate of P2 and this coordinate of P1, because they are reference triangles of one another, should be the same values, just different coordinates within the coordinate plane. Okay, for example, if you think about unit or this second quadrant here, technically you're always going to have a negative and a positive value because you're moving left and up. Okay, so if you think about a coordinate plane, if you had a coordinate right here, left and up to get to that coordinate would basically be a value of negative x, positive on the y. Okay. On top of that, this particular coordinate relates directly back to my original triangle. It's basically if I took these two triangles and flipped it over the y-axis, I would get the same picture. Okay. So these coordinates are always going to be related to one another. So one of the key things that we're going to be bringing up is how if I know one value, if I know something on one side, I can solve it for a different quadrant. Okay. Just by knowing this first quadrant, I should be able to find the fourth quadrant coordinate and the third quadrant coordinate based off of this information. Okay. And that's one of the key things we're going to have to truly understand about a unit circle. It's one of the important things that we're going to talk about just in general about this example. If I know an answer from the first quadrant, technically I can use that same answer to find problems within the second, third, and fourth quadrant. Okay. So with that being said, let's go ahead and discuss how a problem like this would look. Okay. In a typical example, basically, if we just read this example right here that they give us, basically say if I give you a 12-degree angle, okay, in standard position that intersects unit circle with the coordinates here. Basically, what they're assuming is that on the terminal side of the 12-degree angle, the points of intersection for the terminal side of the other three angles can be found, right? So basically what this is telling us is that if I have a 12-degree angle, technically I can find every other angle of that triangle. If we truly think about this, here's my unit circle and here's my coordinate plane. Technically a 12-degree angle going to be very small is going to be right about here, right? Well, that's going to give us that coordinate of 0.978, and the value of 0.0 or 0.208, right? Well, technically, if I know that coordinate, I could use the same exact value and flip it and create a triangle right here. But we have to understand, how does that reference triangle relate? Well, if this is a 12-degree angle here, then we want to assume that this is a 12-degree angle here. Well, how do we get a 12-degree angle there? Because technically, we can't measure that angle. We have to measure the whole thing from our initial to our terminal. Okay? Well, the easy way to do that is to understand that a 168-degree angle has to be the same, right? Because to get a 12-degree angle built into a triangle here, I would have to basically subtract 12 from the 180 mark to get that original value. Okay? Same thing could be said about the bottom of this triangle. If I wanted to find a third quadrant, I would need to find basically from original all the way down to that actual terminal side, which in this case would just be 180 plus 12. Okay? So I can always reference back to these reference triangles and these reference angles based on this idea of the unit circle. So once again, let's try to look at one that might kind of describe to us how to find these out. Okay. So here's kind of the reference idea behind it. Okay. First and foremost, they basically tell us these particular values, right? Where let's go look at letter B. Given that cosine of pi over 12 equals square root of 6 over, square root of 6 plus square root of 2 over 2, find the exact values of cosine of 11 pi over 12 and 23 pi over 12. Now, we really are trying to look at this problem as not necessarily like a find this exact answer, plug it into cosine and solve it out. What we're really using it as is referencing how this is going to be looking throughout this example. Okay? Technically, pi over 12 references 11 pi over 12, and they also have another reference angle at 23 pi over 12. So we want to talk about how is this actually affecting my answer as a whole. Okay? So if I were to look at this, first and foremost, I want to assume because cosine is here, we know cosine has to deal with the x values. So when we're thinking about this actual graph here within a coordinate plane, if 11 pi, or excuse me, if pi over 12 is going to be a very short terminal angle right here, 11 pi over 12 has to be related to this quadrant right here, okay? This could be pi over 12. This one has to be 11 pi over 12. The reason I know that has to be 11 pi over 12 is because if you think about it, this value here is technically pi radians. Well, 11 pi over 12 is very close to that pi radians portion, but it's not necessarily there yet, right? I'm actually 1 pi over 12 away, okay? On top of that, if you notice, look at how it references each other. Notice how these two relate. If I were to combine this value with this value, I would be at pi, correct? So by referencing those, I can then look at the actual coordinate and say, okay, well, how does this relate back to my original problem? Well, if I think about this quadrant has a negative x and a positive y. Well, because I'm dealing with cosine, which is strictly going to be x values, I can look at this answer and basically say, okay, well, the cosine of 11 pi over 12 has to equal negative square root of 6 minus square root of 2 over 2. Because it has to be in the negative quadrant or the negative area of that value. Okay? So all I'm doing is flipping the signs of each of those. Versus, let's say I use the other value. Let's just say I use the cosine of 23 pi over 12. First off, we have to assume what quadrant is that in. Well, when I read that, I'm assuming, okay, if 24 pi over 12 would be 2 pi, which would be officially at this point, that angle has to be pretty close to here. Well, because that's in that fourth quadrant, I know this has to be a positive x with a negative y. So basically, the idea of this one is that if I have a positive x, this value should be the same as the original. Because at pi over 12, I had a positive x. And in the fourth quadrant, I also have a positive x. So I can plot these out and basically say that each of those values, at least for the cosine's sake, has to be the same. Okay? And that's kind of the main idea of this example. That's kind of the main idea of the thing we are looking at, is how we can use these reference angles to really solve out these values and work it out from there. Okay? Next one, let's just look at number 9 here too. Given that sine pi over 10 equals 0.296, find x between pi over 2 and 2 pi such that sine equals 0.296 once again. Okay? So basically, they're telling us that we want to basically get the same answer for sine. Okay? Notice how we want to try to plug in a, we want to plug in an x value that's going to give us the same exact value as the original. That's key. Okay? So when I focus and look at a unit circle, originally, pi over 10 is right about there. Okay, that is your pi over 10 mark. Notice in the positioning of this where this coordinate's at. You're in the first quadrant where you have a positive x and a positive y. Well, understand all the reference triangle is going to do is it's going to change that y value from positive to negative. For example, if I go down into this quadrant, I would have a positive x and a negative y, which means this same exact answer is going to stay the same if I was in that quadrant, or at least the values of it. The only difference is the actual y value is going to become negative because of positioning. Well, in this particular problem, we want to figure out, when is that y value going to stay the same? Well, I have to focus on my three quadrants. If y is positive in quadrant 1, I want to focus on and basically say, where else is y going to be positive? Well, that would lead me into quadrant 2. In this quadrant over here, if I had a coordinate, my y value technically isn't going to change. The only thing that changes in quadrant 2 is my x value, because I would have a negative x and a positive y. Well, when I focus on that, I want to basically then assume, okay, what would my reference angle be to get this same exact coordinate? Well, in this case, I would have to assume if pi over 10 is in relation with this value, how do I relate it back to the triangle here? So basically, what is this angle here? Well, in that idea, if this value is pi, then this angle or this coordinate would have to be pi over 10 less than what pi, or than the actual 180 pi value. In this case, that would be 9 pi over 10 as an answer. At that particular reference angle, I would get the same exact number, which is 2.9 or 0.296, but it is just in a different quadrant, okay? And that's one of the main ideas we're talking about. Now, we'll go more in depth in this in class and answer questions, but that's one of the key things I want you to think about from this lesson. As we use a unit circle, we can always reference all these different coordinates around the graph. It's why when we get specific values, and if I pull up just yesterday's lesson just so we could look at, it's why when we go through specific values and look at them, things always work out so nicely. If you think about a coordinate right here for the 30 degrees, we get square root of 3 over 2 and 1/2. Well, if I use the reference angle, which is 5 pi over 6, look at my coordinates. It's the same exact values when it comes to numbers. The only difference is one of them's negative and one of them's positive. Once again, the reason that is because in this side, because you're on the left side of the coordinate plane, x is negative, but y is positive. Versus on this right-hand side, both are positive because you're in first quadrant. Okay? But besides that, that's all I got for you for today. Make sure you take this opportunity to answer any questions you have or bring any questions to class. Besides that, I will see you on the next class day, and have a great day.